protection. There's just more and more expensive and better protection. Okay, so my goal in our early work, we looked at how to have a trustworthy index over 7 years of documents. So if you have 7 years of documents and you want to find the ones on a particular topic, you cannot do a sequential search. So the easy way to attack these worm servers right now, their indexes are not trustworthy. You just have to alter the index. It's on ordinary storage. Piece of cake. It is fixable. You definitely can fix that problem, but as long as the regulators don't require it, then the customers won't pay for it. The vendors would be happy to add lots of functionality to these products as long as the customers are forced to buy it by the regulators. That was our early work, and then we moved on to database data. And there, just putting the database on worm isn't going to work because we need to mess around inside the file every time the data changes, and that won't work. So here's the basic model. We have a green timeline. We have ordinary storage in yellow. Here's the database, a bunch of transactions run, and we get the current state, which I'll call the final state in this talk. The auditor comes, and the goal of the auditor is to check whether this plus these actions really should be that. That's what they need to do. Even if the system crashed or somebody tried to tamper with the data in the middle. So as a starting point, we're going to use a temporal database that is called transaction time databases. The database community worked on these a lot starting maybe in the 90s. Worked very hard on this, and the idea is very simple, and just like in all systems research, you need a simple idea and then it's hard to make it work. So the idea is when someone updates a tuple, you just keep all versions of it. You never throw away the old versions. So you timestamp them so you know when what time is associated with it. Here's when the tuple was first inserted, then someone updated it, it's got the new timestamp, updated again, updated again, updated again. Here they deleted it, and we don't actually delete it, we just put in a special tuple. So that's the model behind the temporal databases, and all the research is about how to make them run fast. They've gotten really good at these transaction time databases to the point where Dave LeMay, at the last SIGMOD conference last summer in Indianapolis, he assured me it was going to be in the next release of SQL Server, the Microsoft database product. I heard last night at dinner that it didn't make it in. That feature was cut at the last moment. So it's not there, but they made it so fast that it's almost in the products. And why would customers pay for that? Because you can mine all your production data and get value out of your production data. You don't have to wait till it shows up in the data warehouse in a week or a month. If you have it all available right there, you can really potentially do some interesting stuff with it. Okay, and another beautiful thing about this is existing applications run fine. They don't see the old versions. They only see the latest version. And if you want to see the old data, you run a query that has a special clause at the end of it that says as of time 25, and then it'll see the latest versions as of time 25. So it's a really nice piece of work that these people did, and we take advantage of it. And I'll skip over this slide, a little too technical. The idea is simple. We've already had a preview of the idea. Well, in this yellow storage, it's just ordinary storage. We'll keep the database always on ordinary storage. When the auditor comes in and audits it, if they think things are okay, we'll dump a snapshot onto worm. So maybe once a year or so. And we'll have the auditor sign it with a digital signature so that we can tell that what's there really is what the auditor put there. Then we'll run transactions, maybe for a year or so, and then the auditor will come in. Oops, I'm skipping ahead by mistake. We're going to keep the transaction log, which is an important part of any database management system. We'll keep it on this purple worm storage instead of in ordinary storage. comes in, their job conceptually is just to see if all the tuples here plus all the tuples here are the tuples currently in the database state. Because the way this log works, database management systems use something called write-ahead logging. And when a transaction comes along, because it's one of these temporal databases, everything it does looks like the insertion of a new tuple. And the rule is you can't actually change the state of the database until you first put a record on the log saying what this new tuple is that you're adding, and then putting a commit record when the transaction actually finishes. And when you put that commit record, once it's there, it's not gonna go away. Okay. The auditor also has to do some little things that are important, but we already have code that does that just comes with the DBMS. It needs to make sure that indexes are correct and the pages aren't garbled and so on, that type of stuff. But that we already know how to do that, so we don't have to come up with new technology for that. Then if someone has tampered, for example, suppose this transaction number 1 inserted some particular value for a tuple t, and then later somebody doesn't like that, they can tamper with the database state all they want. It's on ordinary storage. They can tamper with that. But once this file is closed, it cannot go in and rewrite the old stuff in the file. So if transaction 1 is already committed, which we assume has happened by the time tampering occurs, then that new value for t is already on here. The commit record for t1 is on here, and the worst the adversary could do would be to put some stuff at the end, claiming that t actually had some different value back at the time of t1. But that's clearly fraudulent, because after something committed at a particular time, it's timestamped. There's no reason to change the values of that transaction wrote. So it's very easy for the auditor to just ignore those things that got appended to the log later. It's clearly fraudulent.
If you're doing write-ahead logging to write-only storage,
Yeah.
and your atomic transaction turns out not to be atomic, fails.
Oh,
You've logged it and it didn't happen.
That's a great. I think you might be the first person that ever noticed that before I pointed it out. So that's really great. That's going to be on the next slide. So hang in just a minute. There's actually several reasons why what I just talked about is not trustworthy or is incorrect, and that's one of the reasons. But first, let me explain the simple version. The main problem with it is the auditor would have to scan a huge amount of data that came in over a year. So we can speed it up a lot if we instead have the auditor hash all these tuples here and add up the hashes. We can, left over from the last audit, we can have a hash of all these tuples, add it all up, using one of these incremental cryptographic hash functions, which means that you get the same value no matter what order you hash the tuples in and add them up. Do the same thing on the yellow storage, as shown by that red arrow. Add them up. Compare the sums, and they should be the same. So that's a lot faster than trying to recreate what a whole year of transactions did. It's a lot quicker. Is it fast enough? Well, I think it's not fast enough. People argue with me that it is fast enough. We'll come back to this point at the end. Okay. And then when the auditors computed this sum for the yellow storage, the audit is successful. You write out a new snapshot and save that sum so you don't have to recompute it.
Can we go back a slide, please?
Sure. no good if the purchase order is legitimate, but then this weird stuff happening at the software level. And vice versa, it's no good if everything's totally trustworthy, maybe up through the database management, even up through the purchase order entry system, but people are putting in fake orders for helicopters. In fact, nobody ordered a helicopter. So from the database point of view, we can't decide whether Qantas really ordered 5 helicopters. The way Sarbanes-Oxley works, you're supposed to have controls at all levels of your organization, focusing mainly on the ones where there's the most risk. So helicopter orders would be a good example. And just because what I'm doing here automates things for the database level, and what the storage industry has already done automates a lot of stuff at the storage level, you still have to have the higher level checks in place. Because I can't tell whether a transaction is legitimate or not. I just do what it tells me to do. Because I can't judge from inside the database. That's a very good question. But it does make life easier if the lower levels of the system, you can trust that they'll do what they're supposed to do, and then you only have to worry about, okay, is that higher level stuff fraudulent? So it makes life a little easier. Okay, so the first reason this model doesn't actually work is that sometimes transactions don't commit. Oops. So maybe T1 is inserting a value for T just like before, but it doesn't commit and it aborts. Somebody pulls their ATM card out of the bank machine and the transaction has to abort. Okay, well, unfortunately, some of the stuff T1 was doing may already be on the log, may already even be on these yellow pages. And why is that? Because sometimes you run out of memory, and then even though the memory is still being used by transactions, you have to throw out some of those pages for other transactions to be able to get some memory. So you pick a victim, which might be one of the pages of T1, where they're writing T. And the rule is, with write-ahead logging, before you can really throw that page out and put it in the yellow database state, you have to put a log record on saying what you're up to, and then you can put it out in the yellow state. Then if T1 later aborts, that information is already in the purple storage. It's not going to go away. That means the auditor's job, well, the code for the auditor is a little bit more complicated. You have to